Hello everyone. My name is Yongxin Fu. I'm the TA of this course. Welcome to the tutorial session of this. Uh, so let's begin. Uh, First, let's see the question one. This question is to determine if the following language is regular. If so, draw its DFA or NFA. I'll give you 10 minutes for solving it. Hello everyone, let's see the solutions. For the question A, the language L is regular because W belongs to the set A and B. So W equals A or W equals B. If W equals A, L equals this, and if W equals B, L equals this, and so the language L belongs to this set, and combine them together, we get this, and the DFA is drawn according to the expression of language L. For the question B, the language L is not regular. The reason is shown in the later slide. Any questions? If no, let's move to the.
I had a quick question there. Just for the quiz, would we just have to show the NFA, or do we have to show kind of the writing that you did there for question A?
Can you repeat your question?
Yeah, for sure. For the quiz, if we received question A, would it be sufficient to just do the NFA, to just draw that? Or would you also like us to write out kind of those steps that you have? Does that make sense?
You can do it according to the question. If the question only needs you to draw the DFA or NFA, you can just draw it.
Okay, that's great. Yeah, thanks a lot.
Okay. So let's move to the question 2 and 3. The question 2 is to describe the language accepted by the following DFA, and the question 3 is for the following regular expressions. You need to give two strings that belong to the language it generates and two that do not. I'll give you 10 minutes for solving them. Hello everyone. Let's see the solutions for the two questions. For the question B, we can see that in the DFA of this language, it has two branches. The first branch is this, and this is the second branch, and the first branch represents the string AA, and the second branch it has a self loop. When you see a self loop, you need to consider the star operation, and the second branch represents this string. So the language is shown like this. And for the third question, for the first question, the two examples of accepted strings are shown here, and two examples of strings that are not accepted are shown here. And for the second question, this language has exact two strings, which are BA and BA, and two examples of the strings that are not accepted are shown here. Any questions?
Yeah, I have a question. For question 3.1, why is ABB accepted, and why is like BBB not accepted?
Because the star operation allows that this is accepted by the star operation. So ABB is accepted.
Oh, I see. Okay, that makes sense. And then why is the triple B not accepted? Because you need doubles.
You can yes, because the beats appear in pairs, so the number of beats in front of A is always even.
Okay, I see. Yeah, that makes sense.
Okay.
Hey.
Any other questions? If no, let's move to the.
I have a quick question.
Okay.
For question number 2, what happens if you're in the top right state and you receive a B?
Can you repeat your question, please?
Yeah, for sure. If you're in the, like, say if you're in the bottom left state and you receive an A, then you just stay in that state. For the top right state, if you receive a B, what would happen? Looks like Austin's saying that you fall off the DFA. Is that right?
If it accepts B, this DFA shows only part of the full DFA. In fact, something are not shown. If it meets B, it will move to a state. However, this is not accepted state. So there is no need to draw it.
Okay, awesome. Thank you.
Okay. Any other questions?
I have a quick question regarding the quiz. What will be covered exactly for the quiz, or do you have no idea?
I have no idea.
Okay.
I have not talked about that with the professor.
And one other thing, are we going to have access to this recordings after, or will this be the only time you would have access to these videos?
Can you repeat your question?
So, are we going to have this tutorial session recorded and be submitted to our YouTube channel, or is this the only time that we will have access to this material?
The video will be uploaded to the YouTube channel.
Okay.
As professor.
All right, thank you.
Okay. Any other questions? If no, let's move to the let's move to the question 4. This question is using the alphabet composer of A, B, and C to create a DFA or DFA that recognizes the set of strings containing no more than 3 A's and no B's. I'll give you 10 minutes for solving it by yourself. Hello everyone. Let's see the solution of this question. For this kind of question, you need to first think about how many states you need. For this question, 5 states are needed, representing no A or B, 1A no B, 2A no B, 3A no B, and at least 1B and more than 3 A's respectively. And for example, the first state represents there exists no A or B, and because C is also in the alphabet, but the question doesn't have any constraint on the number of states. So we can say that there exists self loops of states here, and there exists 4 accept states referring to the first 4 scenarios. Any questions?
Yeah, I have one actually.
Okay.
So in the diagram, the bottom state is a dead state, right?
Yes.
So,
yes.
Okay. Could we omit that for simplicity? Just kind of like how on previous examples, we did not include a dead state?
Okay. That's fine.
Okay, thank you.
Okay. Any other questions?
So in the language that we are worrying about, we essentially don't even have to worry about having A or B essentially, right? So we could technically make a DFA that would be a singular C that is a repetition. Wouldn't that be a correct statement?
I'm sorry, can you repeat your question?
So in the language ABC, the NFA or DFA recognizes a set of strings containing no more than 3 A's and no B's, right?
Yes.
So that means we have to have less than 3 A's. But would that be a requirement, since we could technically only have the start state, which is a final state as well? So would that be a valid result, since technically speaking, we don't really have to have 3 A's, right? So
no. The question requires you to create a DFA that record.
all of them. Okay, never mind.
Yes,
Yeah.
all of them.
Okay.
Otherwise,
Okay.
the question will be.
Yeah, it will be a specific one. Yeah.
simple.
Yeah. Okay. All right. No worries. Thank you.
Okay. Any other questions? If no, let's move to the. If no, let's move to the question 5. This question requires you to that with the alphabet A and B is represented in this regular expression. You need to construct the associated epsilon NFA. I'll give you 10 minutes for solving it.
और पी स्टार का मतलब है मैं 01 बनाओ 01 का तो ए बी कितनी बार भी no fucking idea mate plus is on no?
Hello everyone, let's see the solution of this question.
What the fucking?
For this question, we can see that the regular expression is composed of 3 atoms. So for each atom, we create a branch for it. For example, this, and the star operation is achieved by using the self loop, and the plus sign means that at least one. So it's different from the star operation, and you need to make sure that at least one pair of A and B is accepted. So any questions? Okay, if no,
could you explain how?
Okay.
Why do we start off with the empty strings? Like, why can't we start off with anything else?
Because
So,
the regular expression is composed of 3 atoms. So we need a starting state, and to use this epsilon arrows pointing to each atom.
So my question is, why can't we just say from start A, arrow A, instead of epsilon, then the endpoint B? So for the first layer, the first like the one we go up epsilon, then right A. Then
Can I help?
Oh, okay.
The regular expression is AB star or AA or AB plus. So you have 3 different accept states that could happen, and you have to test for them all at the same time. So the epsilon in the NFA goes to each branch at the same time.
Right, but I'm asking what's the reason for the epsilon?
Because you have to test all 3 conditions at once. So the epsilon just takes it and runs all 3 branches parallel.
Okay.
A cool way of thinking about it is like if you see a plus in these expressions, like it's 3 distinct terms, that's a great sign to use an epsilon transition right off the bat.
Can you repeat your question?
So mine?
I'm sorry, I didn't hear it very clearly.
Are you asking to me? Like, I understood why we're using it now. So it will be for the or statement, essentially speaking. So, okay, I understand. The guys in the call helped out. So it's okay. Thank you.
Okay. Any other questions? Okay, if no, let's have a short break for 5 minutes before entering the session of pumping lemma. Hello everyone. Let's move to the section of pumping lemma. The pumping lemma is that if L is a regular language, then for all string belongs to language L, where mod S is greater than or equal to P. P is a number called the pumping length. Then S can be divided into three parts, X, Y, Z, where for all I greater than or equal to 0, X, Y to the S and Z belongs to language L, and mod Y is greater than 0, and mod XY is less than or equal to P. The pumping lemma is utilized for proving a language is not regular, and the process to prove that language L is not regular using pumping lemma is achieved by proof by contradiction. There exists 5 steps. The first step is to assume that L is regular and P is the pumping length. And the second step is to select one string S from language L, and mod S is greater than or equal to P. And S should be carefully selected according to the question to simplify the proof process. And the third step is to is according to the pumping lemma, S can be divided into the three parts X, Y, Z, and the three conditions should be met. And the fourth step is to prove that there exists one I to let X, Y to the S, Z doesn't belong to L, and this is a contradiction, and hence L is not regular. And I need to emphasize that what we need is the rigorous proof process, not the conclusion. And a common mistake made by students is to assign real values to P, X, Y, Z for proof. For example, assigning P to be 2 or 3. This is wrong. You cannot assign real values to P, X, Y, Z for proof. We don't know their real values, and the pumping lemma doesn't give you the power to assign the real values of P, X, Y, Z for proof by yourself. First, let's see one example. This question requires using pumping lemma to prove that the language L is not regular. We can prove it by using the 5 steps shown in the last page. The first step is to assume that L is regular and P is the pumping length. Then we need to choose a specific string S from L. Here we can choose the string S equals 0 to the piece, 1 to the piece. Then the mod S equals 2P, which is greater than P. According to the pumping lemma, S can be divided into X, Y, Z, and the 3 conditions needs to be satisfied. Then we think about the different cases. The first case is that y contains all zeros. In this case, xy squared z contains p plus mod y zeros, which is greater than the number of ones. This is so the string xy squared z doesn't belong to language L. This is a contradiction. Hence, L is not regular. Then we think about other cases. According to the pumping lemma, the mode xy is less than or equal to p, and the string s begins with p zeros. Then xy must be contained entirely within the zeros part of string s. Therefore, y must contain only zeros, and there exists no other case for us to consider. So in conclusion, L is not regular. This is the rigorous proof process. Then let's move to this question. Using pumping lemma to prove that language L is not regular. This is an example we used in the first question. I will give you 10 minutes for proving it. Hello everyone. Let's see the proof process of this question. The first step is the same as that used in the last question. Assume that L is regular and P is the pumping length. Here, one proof technique is to utilize some languages already known to be non-regular to prove that another language is not regular. Here, we choose the string W to be 0 to the piece and 1 to the piece. And we know that this language is not regular according to the previous question, and so S equals WW equals this, and therefore mod S is equal to 4P, which is greater than P. According to the pumping lemma, S can be divided into 3 parts X, Y, Z, and the 3 conditions needs to be satisfied. Here, we also divide the scenario into different cases. The first case is that Y contains all zeros. We can see that this part of proof process is very similar to that used in the last question, and here we also only have one case that Y contains all zeros, and so and the contradiction is found, and in conclusion, L is not regular. Any questions?
So I'm assuming this is an example for when I is equal to 2.
Yes, you can
Sorry.
assign any integer values to I for the proof process.
Okay, yeah. Basically, any I except for 1 would work in this case, right?
Yes.
Awesome.
Any other questions? If no, let's move to the next question. Using the pumping lemma to prove that language L is not regular. I'll give you 10 minutes for proving it. Hello everyone. Let's see the proof process of this question. The first step is to assume that L is regular and P is the pumping length. Here we choose the string S to be 1 to the P squared. Therefore, mod S equals P squared, which is greater than or equal to the pumping length P. According to the pumping lemma, S can be divided into X, Y, Z, and the three conditions need to be satisfied. And we and the X, Y squared Z equals 1 to the P squared plus mod Y. And because P squared is less than P squared plus mod Y is less than or equal to P squared plus P. It's less than P plus 1 squared. So P squared plus mod Y is not a perfect square. Therefore, X Y squared Z doesn't belong to language L. This is a contradiction. Hence, L is not regular. Any questions? Okay, if no, let's move to the question 9. I'll give you 10 minutes for proving it.
Hi, I have a quick question about the last pumping lemma proof. I guess it would apply to this one as well. Do we always assume that n belongs to the integers?
Yes.
Okay.
Hello everyone. Let's see the proof process of the question 9, and this proof process is very similar to the previous question. The first step is to assume that language L is regular and P is the pumping length. And here we choose that string S equals 1 to the 2 to the P's. Therefore, mod S equals 2 to the P's, which is greater than P. According to the pumping lemma, S can be divided into X, Y, Z, and the three conditions need to be satisfied. And X, Y squared Z equals 1 to the 2 to the P plus mod Y. And because 2 to the P is less than 2 to the P plus mod Y is less than or equal to 2 to the P plus P is less than 2 to the P plus 2 to the P equals 2 to the P plus 1. So 2 to the P plus mod Y is not a power of 2. Therefore, XY squared Z doesn't belong to language L. This is a contradiction. Hence, L is not regular. Any questions? Okay, if no, let's conclude today's tutorial. Good luck for tomorrow's quiz. Thank you.
Hi, I actually just have one quick question.
Okay.
Do you know of any other tricky or complicated, like pumping lemma structure questions that you think confuse most undergrad students when they're first learning this? I know we covered the whole, like, basically anything to the power of n kind of style. We covered the repeating strings kind of style. Just wondering if you know of any other, like, really tricky pumping lemma questions that might be good to dive into.
Currently, no.